All right, so here's our topic, and here's our objective, Dr. Square and his balloons. And what it means is if you've got two different gases, either they're different types of gases or they've got um, a temperature, what's that going to do to their speeds, their kinetic energies, or their velocities? All of them are going to be a bell curve, but we're going to talk about what's going to happen to the bell curve. All right, here is a definition, and keep in mind it's a probability. So this is, like this is what's most likely going to happen. They're going to be, in any given system, there'd be variance. All right, we're going to use PhET to do this. And here's PhET, and I've got this all queued up. So now we're gonna add the gas. Oops, wrong one. And we're gonna add the gas, and then we're looking the first thing we want to look at is temperature. What happens to this curve? All right, you can see I've got a nice curve here. I've got a range of speeds. All right, and you can see that in this simulation, these range values are going up and down, and the same thing is happening with the kinetic energy. All right. Now, what would happen if I heat it up? What's going to happen to this graph? So you'll notice that the graph is kind of shifting to the right. All right, and it's also flattening out. All right, so that's what's going on. So when I have a cold gas and I heat it up, what happens to its speed, its kinetic energy, its range of these values? It's going to go up. All right, and that's what it's going to look like. So what is this showing us? That it's directly proportional. All right, and it's also showing us that this graph is going to flatten to the right. Now the area under both of these graphs, if I took the integral, would be the same because I'm not changing the number of particles. I'm just changing the peak of the peak of the curve and like the shape of the curve, so to speak. All right, now the next thing we need to look at is when we've got two different gases on there. Now you'll see right down here, the red is less massive than the blue. So let's play it. So now you can see that this, in terms of speed, the red has got a much larger range of speeds and the blue has got a much narrower range of speeds. And once again, you have a wide range of speeds. If you watch, you've got some little molecules going really slowly and some molecules going really fast. All right? So what that means is this is for the last one. If I start with a heavy gas and I lighten it, the curve is going to flatten again. All right. Now I did this as an inverse change, so we're going to talk about it in the other way. Like if I increase the mass, the graph's going to go from this to this. All right. So the range of these things would go down. So that's inversely proportional, and the curve rises to the left. All right. Now here's an example of this. You've got some you've got four noble gases, all right? And this is why if I had a balloon and I had some helium in there, and if I also had some xenon is moving a lot slower than the helium. Therefore, the helium would be much more likely to get out simply because it's going to reach the surface of the balloon much faster, which is like totally radical. Because it's smaller, you're going to have more particles that are going fast as opposed to xenon, that has like very little going that fast. So the probability of some helium hitting the walls is much greater, and therefore a lot of them will, and some will actually get through the walls of the balloon. Here are my sources, and I wanted to talk about one of them, and I'll post these in the description of my text. Thanks, PhET, for letting me use their simulation. So here's one of the images that I kind of flew over. This is for increasing the temperature. You can see that for different samples of nitrogen, as you go up, the cloud, the curve flattens and moves to the right. All right. Thanks so much, and I hope this has been helpful.